So in the previous session we have discussed about conditional probability. Okay, probability of A given B means already B has occurred. Okay, so we are saying that was nothing but probability of A intersection B divided by probability of B. Okay, so that is the conditional probability. That is one need to know about conditional probability before approaching Bayes theorem, which is one important theorem in probability. Okay, so then after completing this conditional probability, will there is another theorem, that is the multiplication theorem in probability. Okay, we'll just quickly go through all that.
Independent event.
Multiplication theorem in probability. Okay. So what is multiplication theorem in probability? Okay. So let let E and A be two events with sample space S. Okay. So E and F are two events with sample space S. Okay. S. Clearly, the set E intersection F denotes the event that both E and F have occurred. Okay. In other words, E intersection F denotes simultaneous occurrence of events E and F. The event E intersection F is written as EF. Okay. So very often we need to find the probability of event EF. For example, in the experiment of drawing two cards, one after the other, we may be interested in finding the probability of the event a king and a queen. Okay. So the probability of event EF is obtained by using the conditional probability as obtained below. So we know the conditional probability of P given F has occurred. Given F has occurred is denoted by PEF and is given by so we know probability of E given F, that means F has already occurred, is nothing but P of P intersection F
By P of F.
by P of F. Okay, so this is, we know this is the conditional probability. Okay, so the requirement is that P of F is not equal to 0, otherwise it will become like a meaningless. Okay. From this we can write P intersection F is equal to P E given F into P of F, right? This is the P intersection F. Okay. So also we know that P F intersection E is equal to okay. So P F given E, not intersection, P F given E is equal to again P of F intersection E divided by P of E. Right, this is P of F given E. Okay. So P of F is equal to this. Okay. So now we know E of F, E intersection F is equal to F intersection E. Okay, that is valuable. Okay. Thus, so combining 1 and 2. Okay, so from this we know P intersection F is equal to PEF, this one. Then that is equation, intersection F is equal to PEF into F, and here we know, then from this we can make out PF intersection E is equal to PFE into PE, right?
Yes.
So let us say this is equation 1. Say let us say this is equation 2. Okay. So now we know this is equal to this. That means if you equate equation 1 with equation 2, so it will become E of E given F into P of F is equal to P F given E
P of P.
P of P. So this you can find. This is the final conclusion. Okay. Okay. So E intersection F is equal to P into P of F. So P of E. So okay. So you can write like this is equal to this. So finally, you can write P intersection F is probability of E intersection F is equal to either this or this. Okay, P of E into PFE or P of A into PFE. So this is the derivation. Okay, either this or this. That is the probability of E intersection F. Okay, so with this you can solve any number of examples. Okay, then we'll understand what is independent event. Okay, so this is a multiplication theorem of probability. Then we'll go to independent event. What do you mean by independent event? When we call two events are independent of each other, so we'll discuss about independent events. Okay. So this is what we have completed is multiplication theorem in probability. Okay. Probability of P intersection F. Either it can be P of P into PFE or P of F into PEF. E given F. Okay. So now what is independent event? Independent events. Okay. So consider the experiment of drawing a card from deck of 52 playing cards. So we have 52 cards. Consider the experiment of drawing a card from a deck of 52 cards in which the elementary events are assumed to be equally likely. Okay. So if E and F denote the events of card drawn is spade and card drawn is an S. Okay, respectively. Okay. So what is E is
Drawing this.
card drawn is spade. And F is card drawn is S. Okay. So spade is nothing but your this one, right? Your this one. Okay. So this is your spade, and the S is nothing but your the card having that 11, right?
Yes.
That is your S. Okay. So these are two events. Okay. So so what is the probability of E? Okay. Probability of E is there are 13 spades, right? And
13
there are
by
52.
1 by 4.
13 by 52 is 1 by 4. Okay. And what is the probability of F? So probability of F is like you have only 4S and you have 52 cards. So 4 by 52 is your probability, which is 1 by 30.
Yes.
Okay. So these are two things. So also E and F is the event. The card drawn is S of spades. So that like this S out of 4S, this S can be either it can be heart, or it can be club, right? This S can be club, or it can be diamond, or it can be spade, right?
Yes.
So it can be spade. So this 11 can be any of these four, right? So now we want to find the intersection. Like suppose also E and F event. E and F, that means intersection.
Section.
E and F event is the card drawn is a ace of spade. So P intersection F is probability of ace is a spade. So probability of ace is a spade. So that is called probability of E intersection F. So we know probability of E intersection F. Earlier we had probability of E intersection F is how much? It will be only one it can happen.
Yeah.
So that is 1 by 52, right?
Yes.
So so probability of E given F is what? Like F is card drawn is S. So once the card drawn is S, and then it will become like a spade. Okay. After it becomes S, then it is spade. So E given F is nothing but probability of E intersection F divided by probability of F. Right?
Yes.
Probability of E intersection F divided by probability of F. So E intersection F we have got as 1 by 52, and then probability of F is 1 by 13. This becomes 1 by 52 into 13, right?
Yes.
So this becomes 1 by 4. 1 by 4. So probability of E given F. So probability that the card is spade once it is selected as S. Okay. So that means out of 4, you are selecting 4. Out of 4, 1 will be your spade. Okay. You have the 1 by 4. So that you know. Okay. Since P is 1 by 4, PEF, PE is 1 by 4. So we can say that occurrence of F has not affected the probability of occurrence of event E. Okay. Okay. So we also have probability of F. Okay. So finally, how much you are getting it to be? You are getting it to be same as probability of P. Right? That 1 by 4, this 1 by 4 is equal. Okay. So you can say that the occurrence of event F has not affected the occurrence of event E. Okay. Similarly, you can find out probability of F given E. Okay. That also is equal to 1 by 13. You can find out. Actually, that will be 1 by 13, which is equal to probability of F. That also has not affected. Yeah. Right. So thus E and F are two events such that probability of occurrence of one of them is not affected by probability of the other. Okay. Such events are called independent events. Okay. So the probability E and F are two events such that the probability of occurrence of one of them is not affected by occurrence of the other. So that remains the same. So in that case they are called independent events. Okay. So this is an example of independent event. Okay. So then there is so this is okay definition. Okay. So there are some more inferences of this independent event. Okay. Okay. So the definition is two events E and F are said to be independent. Two events E and F are said to be independent if P of F is equal to Pf. Okay. So P of F given E is equal to Pf. If this is the case, then E and F are independent. Okay. Okay.
Yes.
So similarly, probability of E given F, okay, is equal to probability of E. If this is the case, then E and F are independent. Okay. Thus, in this definition, we need to have this denominator need not be null set. Okay. Now, by multiplication of multiplication rule of probability, so we know E F is equal to PE into PFE, right? This is the multiplication rule, right?
Yes.
We have just studied. Okay, then PFE is equal to PF into P given F. So these are the multiplication rule, right?
Yes.
We have just done. Okay, so this is 1, this is 2. Okay, so this you know. Thus using two, the independence of two events is also defined as follows. Okay, so definition is, so let E and F be two events associated with same random experiment, then E and F are said to be independent. So E and F are said to be independent provided P E intersection F is equal to probability of E into probability of F. Okay. So okay, so we have missed one thing here. E given F, F given E. Probability of F given E is equal to Pf. Probability of E given F is equal to Pe. Then probability of P intersection F is equal to Pe into Pfe. Then probability of okay. So probability of we have some different inference we are trying to draw. So E given F is equal to probability of E into probability of F. Okay. So probability
That
of
is the
F
last
given E
thing.
is nothing but probability of F, right? From the first equation, right? So this is 1, this is, let us say this is A, this is B. So from probability of E given F is equal to P, then PFE we know is equal to PF,
Yeah.
right? So
Yes.
so probability of E given F is equal to probability of P into probability
That
of
is
F. So if two events are independent, this is going to happen.
Yes.
Okay. So so this is the so if two events are independent, this is what is going to happen. And I gave you example of independent events. Okay. So there are a number of examples based on it that you can solve. So now you understood what is independent event, and then you have understood what is multiplication theorem. Okay. So there are a good number of examples you can solve. So now with this background we can go to Bayes theorem. Okay. Clear?
Yes.
You can go to Bayes theorem, which is an important theorem in the theory of probability. Bayes theorem is an important theorem. So with this understanding of conditional probability, independent events, and multiplication theorem, we can, with this background, we can understand what is Bayes theorem. Okay. Is it clear?
Yes.
Bayes. His name is Bayes. That's why the apostrophe is after S. Bayes theorem. Okay. 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 So let us have a sample space. Okay. Let us have a sample space. Okay. So this is your sample space. This complete set is your sample space. Okay. Then it will have different events like say E1. Okay. Then it will have another event, let us say E2. Let us say some E3, E4 or whatever. Okay. So these are some of the events, and there is another one, like there is another one. So let us say there is another one, that is the A. Okay. A. Okay. So this is another one. Okay. So let E1, E2, E3 and up to En be a partition of sample space S. Okay, and suppose that each of the events E1, E2, E2 has non-zero probability of occurrence. Okay, let A be an event associated with S. Okay, so so A is also associated with S, and E1, E2, E3 are a partition of sample space S. If this is the case, then theorem of total probability. So there is something called theorem of total probability. Okay, theorem of total probability. What does it say? Probability of A is equal to probability of E1 like into probability of A given E1. Okay, like this.
Yeah.
So, like same probability of E2, then probability of A given E2, right? Given E2, okay. Then it will go on like this it will go on. Then probability of En, probability of A given En. Like this it will go. Okay. So this can otherwise be written as probability of A is equal to sigma j is equal to 1 to n. Okay. Then probability of Ej, okay, into probability of A given Ej. This is the theorem of total probability. So this J you can replace, and then it will be a summation. So this is the theorem of total probability. So why we are studying it? Because it will be useful in Bayes theorem. Okay. So that's why we are studying it. So okay. So with this background, with this background we can so with this background we can go to Bayes theorem. Okay. So what does Bayes theorem? So there are good number of numericals that you can solve based on this. Okay, so there are good number of numericals you can solve based on this. Okay. So you can solve a good number of numericals on theorem of total probability. There are many numericals given based on this. Okay. There are many numericals given based on this that you can solve. Actually, we can try one also. This is theorem of total probability. So using this theorem of total probability, we can solve some numericals also. Okay. So let us say a person has undertaken a construction job. Okay. So let us do one example. A person has undertaken a construction job. The probabilities are 0.65 that there will be a strike. Okay. I think I have already explained it to you, so no need to do it. You have understood it already. Okay. So then with theorem of total probability we will get into Bayes theorem. Okay. What is Bayes theorem? So the Bayes theorem says E P1, E2, N are non-empty events which constitute a portion of a sample space S. So E1, E2, E3 are non-empty events which constitutes of a sample space S. So this belongs to a sample space S. S and E1, E2, E3 are pairwise disjoint. Okay, and so there is E1, E2, E3 are like there is E1 intersection E2 is equal to null. Okay, null, and E2, E3 is equal to null, like that. That is the condition. Okay, E2, E3 is equal to null. This is one condition. They are pairwise disjoint, and another condition is E1 union E2 union E3, like this. En is equal to sample space S. That is another condition, and A is any event of non-zero probability. Okay, so let A is a event of non-zero probability. Then what does Bayes theorem says? Probability of E J, any E given A. Okay, A is another event of non-zero probability. Okay, is equal to probability of Ej into probability of A given Ej. Okay, so A is something some other event. Okay, then divided by summation J is equal to J is equal to 1 to N, J is equal to 1 to N, probability of Ej, probability of A Ej.
Yes.
Okay, so so probability of Ej given A is this one. So that one probability by total probability. Okay. So Okay, so this is the theorem. How do we prove it? Okay, how do we prove it? Okay, so probability of Ej given A. So this is the proof. Okay, proof. Probability of Ej given A is equal to, we know its intersection. Okay, probability of Ej intersection A, right? Right.
Yes.
That is the intersection, or A intersection EJ, or both are same, right? A
Means the
intersection
same.
EJ or A intersection
Intersection is
EJ divided by probability of A.
A.
Okay. Probability of A. So then probability of A intersection EJ that we have studied in the multiplication theorem is nothing but probability of
A into probability of
EJ into
probability
probability
of
of A intersection EJ. Right?
Yes.
That we have probably studied in the multiplication theorem.
Yeah, first thing.
Bayes theorem. For Bayes theorem, we have independent events. Multiplication theorem. Okay, so in multiplication theorem, we have done it like probability of intersection is equal to probability of P intersection F is equal to probability of F that we have studied. So same thing we are applying here.
Multiplication theorem formula.
That is the multiplication theorem formula. So probability of Pj is divided by probability of A. Right? So this is by multiplication rule of probability. Okay. So that is okay. Bayes theorem. Then this is independent from, then multiplication theorem of probability. So then this we get by multiplication theorem rule of probability by result of theorem of total probability. So this remains the same, but the probability of A we have studied by theorem of total probability, and the probability of A is equal to so the denominator will change to Pej into PAEJ. Then PA we have studied the theorem of total probability. The theorem of total probability just now we have done, which is equal to sum of PEJ into PAEJ.
Each.
So that's how you have proven it there. Okay.
Yeah.
So this is the proof of Bayes theorem. Okay. What we have done, like what we have studied in the previous section, like theorem of total probability, multiplication theorem, using all that we have proven the Bayes theorem. So to prove Bayes theorem, we must know what is the theorem of total probability, then multiplication rule of multiplication theorem. So using both things, you have got, okay, this is your Bayes theorem. Okay. So there can be a number of numericals on Bayes theorem also. So we have already done it.
Yeah.
I have just explained you the theory now. So this is Bayes theorem. Okay. So you can solve a good number of examples on Bayes theorem. Okay. Then Bernoulli's. Yeah. So we'll just quickly go to the Bernoulli's. Okay. So I am just giving you quick walkthrough. Okay. So next we'll go to the Bernoulli's. Okay. After Bayes theorem comes your consider random variable and probability distribution. Do we need to go to that? No. Okay. We will go directly to the Bernoulli's this thing. So now we have proven Bayes theorem, right?
Yeah.
Now we will take up on this probability distribution in some other session. Now we will go to the Bernoulli's distribution or theorem. Okay, so now you understood Bayes theorem, and then probably in the next session in 10-15 minutes we will finish Bernoulli's theorem. It may be too much for you, so maybe we will take 10 minutes for Bernoulli's. We will take 10 minutes for Bernoulli's trials and binomial distribution or Bernoulli's distribution. We will take it. Okay. Thank you.